So my name's Jack Baker. I'm just going to get right into it by talking about WebAssembly. So I want to start by talking about what WebAssembly actually is. So you may already be familiar with this, bear with me, but as a little bit of background, developers have done and continue to do a really incredible job of speeding up JavaScript in your browser with stuff like JIT compilers and a million other optimizations. The problem is that JavaScript is such a dynamic language, and that dynamic nature will always be a roadblock for optimizations. There's only so much a JIT compiler can get away with. So what WebAssembly does is it provides sort of a complement to JavaScript in the form of a static, pre-compiled binary format that can be used for like performance-intensive applications, and it's much easier for your browser to optimize. So from a practical sense, what WebAssembly actually is it's basically an instruction set like a simplified CPU architecture that runs in your browser. So WebAssembly is built to be targetable by existing compilers and existing languages, meaning we're finally at the point where we can start writing web applications in C. Awesome. So I want to talk a little bit about what WebAssembly is actually used for. So as you probably gathered from the name of the talk, WebAssembly is used for video games, and this is actually becoming really common. If you look at any of those like old school like Flash game sites, you know, Newgrounds, Congregate, stuff like that, what you'll notice is that a huge portion of the new stuff that's uploaded is actually using WebAssembly as the back end. And that's with good reason. Because the two really common engines that you'll run into these days for video games are Unity 3D and Unreal Engine 4. And both of these engines can now target WebAssembly. So you can build your Unity 3D game, you can click a couple buttons, and it's running in your browser using WebAssembly as the back end. So as a hacker, this means that there's a ton of targets out there. There's not really a lot of tools to interface with them. Just for completion's sake, I should say that WebAssembly is used for a lot of different stuff, not just video games. So like you'll see a lot of like desktop applications that have been retargeted as web applications. Anything 3D is a really good candidate for WebAssembly. Obviously, you'll see crypto miners because we live in a horrible world. And there's all sorts of other stuff. So the reason I say this is that these techniques are not, the techniques I'm going to show are not really WebAssembly, or I'm sorry, not really video game specific. Video games are just really the most common and in a lot of ways the most fun targets you'll run into. So with that in mind, I want to talk about reverse engineering WebAssembly. So the interesting thing about WebAssembly is that it makes web reverse engineering start to feel more like traditional like binary reverse engineering of like ELF files, PE files. For instance, we're back to using a disassembler. So there are a few tools that actually support WebAssembly as is, but it's mostly for static analysis. So there's stuff like Redare2, there's like no chance I'm pronouncing that right. Jeb decompiler has some experimental support for WebAssembly, and then there's some WebAssembly specific tools like the WebAssembly Binary Toolkit or WABIT. But that's mostly static analysis. When we talk about dynamic analysis, the story changes a little bit. If you're talking about debugging WebAssembly, you're probably talking about using your browser. And if you've used the debugging tools in your browser for WebAssembly, you've probably noticed that they're pretty lacking. So you'll see that there's no like watch points, there's no conditional breakpoints, and there's a ton of random bugs. So with that in mind, I want to talk a little bit specifically about what video game reverse engineering is. So video games are actually a really unique challenge when it comes to reverse engineering, and this is for a couple of reasons. The first is that video games compared to like other types of applications are so much more complex. Because when you're looking at a video game, you're not looking at just the code that the game developer wrote. You're looking at the entire game engine, you know, the graphics, the sound, physics, everything like that. It makes for so much code to look through that it can be daunting. The second thing is that video games are, of course, more performance intensive than most other applications, and performance impacts are a lot more noticeable. If you're using some, you know, dynamic analysis tool and it's slowing down the game, no one wants to play a game at 5 FPS. It just doesn't work. So there's an extra challenge when you're developing tools for dynamic analysis or hacking video games. So with that in mind, when I started looking at hacking WebAssembly games, what I was really looking for was a tool like Cheat Engine specifically for WebAssembly. So I want to talk about what Cheat Engine is. If you haven't heard of Cheat Engine, you probably didn't play MapleStory growing up. But what Cheat Engine is it's a tool made by a guy named Darkbyte, and it's effectively a specialized debugger specifically for hacking video games. So what Cheat Engine can do is it can search memory, it can modify memory, it can freeze memory, meaning that attempted changes to that memory location won't take. It can use watch points, and it can inject or patch code in the binary. So that sort of makes sense, but to understand why Cheat Engine is so cool, why it's worth trying to emulate these methods, I want to go through sort of a 101 example of using Cheat Engine. So with that, imagine we're playing our game, and our goal is to make our player character invincible. And the one thing we do know, we haven't done any reverse engineering, but the one thing we do know is that our player currently has 5 health. So what we do is we ask Cheat Engine, look for everything in memory that has the value 5. And Cheat Engine comes back and it says, okay, I found a few thousand places where I found the value 5. That doesn't quite narrow it down. It's still too much to look through by hand, but it starts to narrow it down. And so what we can do then is we cause our value to change. We get hurt. Now our health value is 4. And we search for that and we say, okay, of all those values that used to be 5, which ones are now 4? And we narrow it down some more. And then we continue that process as many times as we need to until we've found the one value in memory that is associated with our health value. And once we've found that memory address, we can manipulate it. We can heal ourselves back to full. We can give ourselves more health than we're supposed to have. We can even freeze our health so that basically any attempt to change it, decrement our health when we get hurt, doesn't take. It just goes back to 5. So just like this, with just a couple pretty quick steps, we were able to go from knowing nothing about this application, no reverse engineering, to doing something practical. We were able to find some value and manipulate it. The problem with this method is that it can take a little while, and it needs to be redone every time we play the game. Odds are the next time we start up the game, our health value is going to be somewhere else, either because of address-based layout randomization or just the fact that dynamic memory mapping is not really predictable. Basically, we probably have to start from scratch every time. So ideally what we want to do is just do this once and then make some permanent change so that we don't have to go through this process every time we want to do this to the game. So the next step we take is we set a watch point on our health address, and then we get hurt again to trigger it. And then Cheat Engine comes back and it says, something tried to write to this value in memory and it occurred right here. And so basically we're able to see exactly which code is responsible for causing our player character to get hurt. And what we can do once we find that is we're able to patch it out. Basically take out the ability for our character to get hurt. And so with that, we've made a permanent change to the binary so that our character is now invincible. So the reason that I go through this example is that it shows that not only is Cheat Engine helpful for hacking video games, we made our character invincible, but it's also a huge help when we're talking about the reverse engineering process. Like we said, video games are dauntingly large as far as applications go when you're talking about reverse engineering. So going through this process, we were able to narrow down this gigantic code base and associate a value in memory with its purpose, and then associate that value in memory with the code that affects it. We were able to really easily find the relevant code without doing a whole ton of work. So this is what's so cool about Cheat Engine. So with that in mind, I had the question of, well, could I apply these same techniques to WebAssembly? And you run into one really big roadblock when you try to do that, and that's that WebAssembly doesn't have watch points. And that was a big part of the Cheat Engine process was using watch points. So my question was, can we emulate the behavior of watch points without them being supported by the spec or by our browser or anything like that? So my first attempt at doing that was basically the dumbest, simplest thing I could come up with, which was just use your built-in browser debugger, put a breakpoint at every single load or store instruction in WebAssembly, and then when that breakpoint is hit, do some math to check if that access is going to affect the address we're watching. And this amounts to thousands upon thousands of breakpoints in any decently sized video game binary. So as you can probably imagine, didn't work at all. Browser basically becomes completely unusable. X kill Chrome, start again, no chance. So I started thinking, if I wanted to do this in a way that wasn't like stupid, what would that look like? So from like a high level perspective, what I came up with was, if we want to emulate the behavior of watch points, what we want to do is inject code into the binary at every single memory load or memory store instruction. And what that code's going to do is it's going to check if that access is affecting a memory area that we're watching, our watch point address. And if it does, we want it to call a breakpoint, call our code to basically alert us that this change was made, maybe give us a stack trace, something that tells us something tried to change our memory address and it occurred right here. So to do all this, we need to employ some form of binary instrumentation. So let's talk about that term a little bit. So binary instrumentation basically is the process of manipulating an application binary, whether that's an ELF, a P file, whatever, to aid in some form of analysis. So there's a lot of really cool binary instrumentation tools that already exist for other types of binaries. So like Frida is an awesome tool for ELFs, PEs, Android applications, stuff like that. Dynamo Rio is another real cool tool. I'm sure there's others I haven't used, but this is not like a new concept. I'm not coming up with the concept of binary instrumentation. There's even some existing tools specifically for WebAssembly. So I want to talk about those a little bit. The first one I want to talk about is a tool called Wasabi by Daniel Lehman. I hope I'm pronouncing that right. And it's a really cool instrumentation and analysis tool specifically for WebAssembly. Unfortunately, it doesn't really fit our needs for a couple of reasons. The first is that Wasabi is written in Rust, and it's intended to be run from the terminal. So if we want to instrument some WebAssembly binary, what we have to do is we have to download it, we instrument it from the terminal, we upload it again, and then we run it. And that's a little annoying. Potentially we could modify Wasabi and compile something that could run in the browser, but then we run into our second problem, and that's that Wasabi does all of its analysis by injecting JavaScript into the binary. So basically, Wasabi will put calls into the WebAssembly binary to JavaScript functions in order to do its analysis. And in testing this, it became really clear really quickly that if we want to run a game at any decent performance at all, we need to call JavaScript as infrequently as we can. So basically, if you imagine the WebAssembly VM and the JavaScript VM are two different virtual machines, and calls between the two are still a little bit performance intensive. And if you're talking about injecting code at every single memory load or memory store instruction, this just becomes completely overwhelming for the browser very quickly. So unfortunately, Wasabi didn't work for us. Let's look at our next tool, which I've actually already mentioned, which is the WebAssembly Binary Toolkit, or WABIT. So WABIT is a library specifically for modifying and parsing WebAssembly binaries. There's even a version of it that's been compiled to JavaScript. So it seemed like the perfect starting point for doing this type of manipulation. The problem is that in reality, when you try to use WABIT to parse like a video game binary, it just takes way too long and way too much memory. So I tried this with like a demo Unity 3 binary, nothing too big, basically just hello world of Unity. And what you would see is WABIT would spin its wheels for 10 or 15 seconds and then just crash with an out-of-memory error. So already we're seeing it's taking way too long. 10 or 15 seconds is way longer than we want to wait, even if it worked, but it didn't. It's running out of memory. Who knows how long in the parsing process. So after looking at the two tools I could find, I sort of drafted a set of prerequisites for what we would want in a tool that we could use for our purpose. So the first thing is we want to be able to instrument binaries from within the browser. We don't want to have to download something, instrument it, put it back up. That's boring. It also needs to be able to handle large WebAssembly binaries. Video game binaries are very commonly like 40 MB plus. It needs to be able to do this quickly and without running out of memory in the process. So since, as far as I know, this tool didn't exist, I developed my own library, which I very creatively titled the WebAssembly Instrumentation Library, or WAIL. And this is WAIL is a JavaScript library specifically focused on making targeted modifications to WebAssembly binaries. So if you think of a WebAssembly binary kind of like an ELF file has sections that have different purposes, and so does a WebAssembly binary. So what WAIL does is it can add entries to any section of the binary. It can edit existing entries of sections. It can also add or remove sections from the binary. So WAIL actually uses a couple tricks to modify binaries quite a bit faster and with a lot less memory usage than other libraries. The first one's kind of a no-brainer. WAIL only parses the sections or elements of sections that are necessary to perform the modifications you defined. If you're doing some modification that doesn't require parsing the code section, it's not going to parse it. It just skips it, and that saves a ton of time right off the bat. The second part is a little bit more complicated. So what WAIL does is it parses binaries basically as a stream. And I want to explain a little bit about what that means. So if you're talking about parsing some sort of binary, whether it's an application or an image or whatever, the normal way you do that involves, you break that binary up into its pieces, you create a map of all those pieces, and then once you've got that map created, you change the parts you want to change, and then you stick everything back together into one big binary. This is convenient, it's straightforward, it's sort of the obvious way to parse a binary, but it's also sort of slow and a little bit more memory intensive. And the reason for that is that you have to split the binary up, store every single piece as a different object in memory with all the memory overhead that might entail, and then do the work of putting it all back together. It takes a little while. So what WAIL does is, as I mentioned, it parses binaries as a stream, meaning it handles and modifies every single element as soon as it's read. Basically, it goes through the binary from the start, reading only one element at a time, changes it if it has to, throws it away if it has to, and then it moves on to the next one, forgets that last element ever existed. This way we don't ever have to do the work of storing the entire binary and all its pieces in memory at once. We're just working with one single element at a time and then forgetting about it once we move on to the next one. There are some downsides to this approach. The first one is that the parser can never go backwards. Once we've finished parsing past a particular element, we've stopped looking at it, we can't go back and we can't make changes to it. We have to do everything we need to do to that element the second we see it. So to deal with this, we have to define all of our modifications before we start parsing. There's no moment where we can parse the entire binary and then say, okay, I want to change this or that or whatever. We have to define everything up front and then let the parser run with it. This sort of causes a second problem, which is sort of WebAssembly specific. So when you're talking about modifying a WebAssembly binary or making additions, there's a lot of cases where making one addition or making one change will rely on information about another section or another element. So I want to give the example of adding a new function into a binary. So you're adding a new built-in function that can be called from the WebAssembly VM. This is actually a three-part process. The first thing you got to do is you define a new element in the type section, which says this is a function. It takes two parameters. One is an int 32. The other one's a float 32. It returns one value, and that value is also a float 32, something like that. The next thing you have to do is you add an element into the function section, and this basically declares your function without defining its body, without defining the instructions that actually make up the function. And when you create this function section entry, you have to reference the index of your new type section entry. So if that new entry you've created in the type section is index 1000, your function section entry has to say, I'm a function, I reference type element 1000. And then you have to create an element in the code section that is basically the body of your function, basically the instructions that will be called when your function is called. And this section also has to correspond to the index of your newly created function element, similar to with the type section. So as you can sort of see with this, there's a couple different pieces of information that we don't know up front. We don't know what index our new type section entry is going to be until we know how many existing type section entries this is going to be. So this causes a problem when we're talking about doing everything up front because there's some knowledge that we don't have up front. So Whale deals with this using sort of a special grammar. Basically, every addition you make to a binary, you're given back a handle. And this handle doesn't have a value until the parser starts running, but it can be used to make these complicated additions. So in the previous example, we add our new type entry, we're given back some handle, and then we use that handle when we define our new function entry. And then we use the handle from that new function entry to create our code entry. And basically by doing this, the parser will see these handles, fill in the gaps for us. And so we can do these complex, like chained modifications while still doing everything up front. We still don't have to know anything about the binary before we start parsing it. If you're not already sick of hearing me talk about WebAssembly parsing, there is one more really annoying catch, and this is actually a two-part problem. And it has to do with the function tables and the global variable tables. So if we take the example of like calling a function in WebAssembly, you're not calling that function by its address or by its name. You're calling it by its index into a table. And so that table is created by the engine when it first starts parsing the binary. So basically what the engine does is it takes all the imported functions, all the functions that have been sort of given to the WebAssembly binary by JavaScript, and it puts them as the first elements in the table. So if you have 10 imported functions, the first one will be 0, 1, 2, 3, whatever, all the way to 9. And then it takes all the internal functions, the functions that are actually built into the binary, and it puts them in the table after those imported functions. So the first internal function will, if you have 10 imported functions, the first internal function will be index 10, 11, 12, whatever. And the exact same process exists when you're talking about global variables, whether they're imported or internal. So the problem here is that the second that you add a new imported function or imported global variable, you throw off the entire rest of the table. So if you have, your 10 imported functions and you add one, what used to be function index number 10, your internal function, is now 11. 11 is 12, etc. And that throws off every single call, every function reference. Pretty much the rest of the binary is broken. And the same with global variables. So this is really annoying, but it's actually pretty easy to fix automatically. So Whale fixes this basically by parsing any section that could potentially be affected by this change. And it finds those elements and it says, oh, you're now off by 1, I add 1 to that, in order to fix those references so that you don't have to do the work yourself. So now that we've talked about the boring stuff and we've got our parsing tool, we can actually go back to our goal of emulating the behavior of watch points using Whale. So let's talk specifically about what that process looks like. So the first thing we're going to do is we're going to create 2 new global variables within the binary. And so the first one of those is going to hold the address that we're watching, literally the address of our watch point. The second one is going to hold 2 different flags for us. The first is just, is this watch point enabled? Yes, no. The second one is, how big of a value are we watching? Are we watching 1 byte? Are we watching 2, 4, 8, whatever? Then, once we have that, the next thing we're going to do is we're going to add an import entry. We're going to import a new JavaScript function. And this function's purpose is to be called when our watch point is triggered. And it's going to do the work of alerting us to that fact. And it's going to give us a stack trace or something so that we're able to work backwards and say, oh, that watch point was hit at this address by this instruction. As long as this function is only called when a watch point is triggered, the performance impact of this is negligible. The next thing we're going to do is we're going to create a new internal function. As I mentioned before, this is actually a 3-step process, but we're going to skip over that now. And what this internal function is going to do is it's going to perform the actual logic of our watch point. So it's going to do the math of does this attempted access overlap with the address we're watching? And if it does, it's going to call the trigger function, that JavaScript function we just imported. Finally, we have one more step, which is that we're going to place calls to our watch point function, that internal function we just created, before every single memory load or memory store instruction. So as long as we're really careful about how many instructions we execute every time we check our watch points, we can actually do this with no noticeable drop in FPS. We can still play video games, we can have all this stuff running in the background, we don't even notice it's there. So now that we understand this process and we've sort of filled in the gaps, what I wanted to do was see if I could sort of emulate Cheat Engine for WebAssembly. And so I built another tool which I call Cetus, and it is a browser extension that's basically Cheat Engine for WebAssembly. The name Cetus comes from the Latin word for sea monster, so you can probably see the theme I was going for here. So what Cetus does is it intercepts and instruments WebAssembly binaries in your browser on the fly before they're executed. And that instrumentation consists of adding reading and write watch points. It adds the functionality to freeze memory, making it so that attempts to change some value in memory don't take. And it can apply patches defined by the user. So we can do code patching, change code through this extension. Excuse me. So with that in mind, I want to get to my first demo, if I can figure out how to use this. Okay. So this is just a really simple demo Unity game, and our goal here is we're going to make this red tank here invincible. So the first thing we want to do is we know that this tank is at 100% health. So we can guess that its health is stored as a float value of 100. So we're going to search for that in memory. We give our value of 100, our comparison of equal, as in we're asking the extension, look for all values in memory that are equal to 100 of type float 32. And we get back 112 results, so we still have to narrow it down some. So what we do next is we cause that red tank's health value to change. So we shoot it, it takes some damage, and now what we're going to do is we're going to search for, of all those values we got last time, which ones are less than 100 now. And this narrows it down. We find 2 of them that are somewhere around 50%, which looks about right. It looks like our tank has something like 50% health. So there's a pretty good chance that one of these 2 is holding our health value. So what we're going to do is we're going to start with the first one. We're going to just bookmark it, and from there we can we've saved the value in memory and we can start to manipulate it. So the first thing we're going to do is we're going to freeze that value in memory. So now what we see is that when we try to change that value in memory, basically our injected instructions basically say, no, don't do that. This value is frozen, that change doesn't take. So our tank is now invincible. So that's a good start, but again, we want to make this process a little bit simpler. We don't want to have to do it again. Oh, I'm sorry, I got a little bit ahead of myself. So what we do now is we want to set our write watch point. Basically, we're asking the extension, tell us what instructions are trying to write to this memory address, or trying to cause the red tank to take damage. And then we trigger it by causing that tank to take damage. And in just a second, we get disassembly of exactly where that code occurred. So we have this function that I'll save you the trouble of reading it. Basically what it's doing is it takes some damage value, it loads our health value, subtracts that damage value from it, and then it stores the new value in memory as our new health value. So what we want to do here is just take out the part where it's storing that new value. Basically make it so that we can't get hurt anymore. I should say that this was recorded on a little bit of an older version of CDIS, so there's some graphical issues here. They're worked out now, I promise. But so what we do is we find this F32 store instruction, this instruction that's gonna write to our new memory address, and we just replace it with a couple other instructions. And then we save our patch. And that's pretty much it. Now the one annoying thing here is that we can't modify code while the binary is running. There's no way to do that within WebAssembly. So what we have to do is we have to restart the game to apply that patch. But as we can see here, we're not using the extension, we're not using CDIS, and even still, we can shoot our new tank and we can see it's invincible. Okay, I'm ahead of myself here. Don't look. Okay. So with that being said, I want to talk about a couple other features of CDIS that I didn't really show in the demo, but the first of those is differential searching. So in the example we just showed, we had the benefit of knowing the starting value we were looking for. We knew we were looking for a float value of 100.